So dear students, so in this video we are going to calculate magnetic field by due to or by due to a circular current carrying conductor. Magnetic field due to a circular current carrying conductor. So we are basically using Biot-Savart law to calculate the value of magnetic field due to a circular current carrying conductor. Okay, let us take a circular current carrying conductor this way. Suppose I current is flowing through this conductor, and let us take R is the radius of this conductor, and we take a very small DL element, small DL element on this conductor. So let us take two DL elements, very small DL elements on the two sides respectively. DL element means very small portion of the circular conductor. Now our intention here is to calculate the magnetic field due to this particular circular conductor at any point P. Let us take at this point P. We need to calculate the value of the magnetic field due to this current carrying circular loop. Suppose this P is at a distance of x from the center of the circle, and let us take, if I join this P from DL, from this DL, and I give R be the distance between this DL element and the point P. And if you see closely, the angle between this DL and this R particular will be 90 degree. This will be my 90 degree. This one, not this one, but angle between this line and this particular tangent to the circle will be 90 degree. So angle between DL and R is 90 degree. So this is to be noted. So using Biot-Savart law, magnetic field due to this DL element at point P will be my dB. So dB is the value of the magnetic field due to this DL element. So and its value will be mu 0 by 4 pi I dl cross this particular R divided by R cube, and the direction of this dB will be towards this direction. So I cannot show you with my right hand rule, but if you see closely, if in this plane containing this R and this DL element and this R, so I make a plane using this DL element and R. So in this plane the magnetic field should be perpendicular, so the perpendicular to the plane will be towards this direction. So the direction of magnetic field at point P will be towards this direction, and DL, angle between DL and R is 90 degree, so dB will be mu 0 by 4 pi I dl R sine of 90 degree, sine of theta, so theta is basically 90 degree in this case, divided by R cube. This R will cancel the cube as a square, so dB will be equals to mu 0 by 4 pi I dl sine 90 is 1. So I dl by r square. So this is the value of the magnetic field due to this dl element at particular point P. Now if I resolve this dB into two directions, suppose one along this direction, which is dB, let us take along x direction, and one along y direction, that is dB y direction, and let this angle be theta. So the angle between dBx and dB is theta. That means dBx will be dB cos theta and dBy will be dB, and let's take magnitude on it, dBy will be dB sin theta from some parallelogram of vector addition. So dBx is dB cos theta and dBy is dB sin theta, because this is the angle between dBx and dB. Now if I do the calculate the magnetic field due to this dl element at the same point, what will happen is it will be directed towards this direction. Another dB will be directed towards this direction similarly. And if I resolve into two components, one along dBy and one along again towards this direction dBx, this dBy will perfectly cancel this dBy. So the only my component remained will be dBx. Similarly, if I take the elements here and here, the y component will get cancelled and only the x component will remain. So for each point or for each line element on this particular circular current carrying coil, the two opposite dl elements cancels their y components. So the only component that will contribute to the total magnetic field at this point P is its x component, which is dBx, and its value will be dB cos theta. So my net field at point P will be dBx. So my net field due to this element, line element dl. So net field due to line element or current element dl at point P will be dBx, which is equals to dB cos theta. So this is the net field due to current element dl only at point P. And we know what is cos theta. If this is theta, you can calculate this will be my 90 minus theta. So geometrically you can calculate it. If this is 90 minus theta, this angle will be my theta. So dBx will be dB. What is cos of theta? Cos of theta is base by hypotenuse. So that is r by small r. And dB we have already calculated. dBx is equals to, the magnitude of dB is mu0 by 4 pi I dl by r square. This is my dB. Capital R divided by, what is my small r? Small r is nothing but small r is hypotenuse, root under of this square plus this square. So this is root under of r square plus x square. Similarly, dBx will be mu0 by 4 pi I dl divided by, what is this r square? This r square is r square plus r square. So r square plus x square, r divided by root under of r square plus x square. So this will give me dBx is equals to mu0 by 4 pi I dl. So it has a power of 1, it has a power of half. So 1 plus half will be 3 by 2. Will be r square plus x square to the power 3 by 2. So this is my dBx. So this is the magnetic field at point P due to line element dl. Now magnetic field at point P P due to entire current carrying circular loop will be B integration over dBx, or closed integration over dBx, and it will be, so if you integrate you will get a net magnetic field. So B will be equals to closed integration of dBx, so dBx is mu 0 by 4 pi I dl r divided by r square plus x square 3 by 2. Similarly, B will be equals to, if you take constants outside, it will be mu 0 by 4 pi I dl, sorry, I r divided by r square plus x square 3 by 2. These all are constants, so root under of dl. So if you integrate dl over a closed circular loop, you will get the circumference of the circle, that is 2 pi r. So mu 0 by 4 pi I r divided by r square plus x square 3 by 2 into 2 pi r. The integration of dl over a closed circular loop will be the circumference itself. So 2 pi into 2 times, and this r into this r will be r square. So B is equals to mu 0 I r square divided by 2 r square plus x square 3 by 2, and the magnetic field will be along the x direction only, that is I direction, because I have taken the only x component cos theta, which will contribute to the magnetic field. So this is the magnetic field due to a circular loop at any point P on the axis of the circle, which will be along, the point P is on the axis. If you look closely, the point P lies on the axis of the circle. Now at center, what will be the magnetic field at the center of the circle? At the center, it will be, at center this distance x will be 0. X will be 0. So magnetic field will be mu 0 I r square 2 r square to the power 3 by 2 along I. So magnetic field will be mu 0 I r square 2 r cube I. This 2 and this 2 cancel, so r square and this 3 will cancel. So B will be mu 0 I by 2r, and which will be along I direction again. So this is the magnetic field at the center of the circular loop, mu 0 I by 2r. And if you draw the magnetic field lines of a circular loop, what you will see is at the axis at the center, the magnetic field will be along x direction, and as you move away from the axis, the magnetic field will be curling this way, this way, this way, this way, this way, this way. So this is the diagram of the magnetic field of a circular loop. It can be also drawn this way. Suppose current is in this direction. Current is given by my 4 fingers. Then my thumb will give me the direction of the magnetic field. So this is current. This is current. So my thumb will give me the direction of magnetic field. So magnetic field will be towards this direction. So it will be straight line at the center axis, as we already calculated. At the axis it will be along I direction, that is straight x-axis, and as you move away from this axis, it will bend like this. It will bend like this. So this is same as of magnetic dipole or bar magnet. So the magnetic field lines of a circular loop and bar magnet are same. Both are magnetic dipoles. So this is for today. Thank you.